Okay, good afternoon everyone. My name's Andrew Leonard, and I'm from the IBM Hursley Lab in the UK, the IBM Runtimes team there, where we work on various technologies, runtimes, OpenJDK, Swift and Node in particular. I'm a technical lead of the OpenJDK team there, and I work with the Eclipse OpenJ9 development team in Ottawa and Toronto, in helping them deliver OpenJDK with OpenJ9 at Adopt OpenJDK. And today I'm going to help explain to you how OpenJ9 can help you be faster, more efficient, quicker startup in a cloud container type environment, and hopefully save you some money at the same time. So, running your Java applications in an ideal world, you know exactly what demands you'd like, and it would be the same all the time, which is a bit of a fairy tale because it isn't. Because then you could just choose the size of server you want, knowing the demand is that forever, and life would be simple. In reality, demand on your applications is random, up, down. Imagine just before there's online sales before Christmas, demand peaks as soon as something decent, or Black Friday, for example. So, you know, in this environment, you need to be able to work with your demand, but also cost effectively and better than your competition, you hope. So, before we get into the detail, just a little evolution of running applications. So the graph here, we can start from a decade or two ago. So the life where things were not very flexible, not very granular, and you just had these big bare metal servers. And if you needed more capacity, you ordered another one, loaded your application up onto it, and hey presto, you had two of them. And the cost and the operating cost associated with that, etc. It's not quite showing the same colours on my screen. Top bit's supposed to be red. It's not red for you, is it? Oh well. Weird. So this big block represents the your big server. As you see, part of the time it's going to be idle, the top bit, which is supposed to be red, is wasted resource usage, money you're paying for but not making use of. And should the unexpected peak in demand come, you're not going to benefit, and your customers are going to be unhappy because their response time is slow, and they'll go elsewhere, etc. Until you buy that other bare metal box. So move forward in time a bit more. Oh, there it is. Sorry, there we go. So move forward a little bit more to the age of hypervisors and basic virtual machines. So we've got a bit more flexibility now, a bit more granular, so we can be a bit more dynamic. So here we can now adjust, the hypervisor, can adjust the demand with a bit more granularity and cater for the dips, so it can take a VM offline or provision another one should there be a peak in demand. Then we go to today with containers managed on the cloud. So there's the world of Docker containers, maybe orchestrated with Kubernetes and Caminera sort of thing. Here now we've got a lot more flexibility, a lot more efficient, cost-effective containers in the cloud. So this is so we can really scale to the demand, and it'll be a lot more cost-effective. So The obvious benefits of running in the cloud, as you probably realise, you can rapidly expand and reduce capacity in response to that demand, as I've just shown on the previous slide, which helps you reduce capital costs and reduce operational costs. The cloud gives us compute on demand. There are those containers coming out of the tap. But the demand is metered. So in your cloud environment, you pay for how many CPUs, how much memory, all those resources you're using. The more you use, the more it costs you. So, that max heap you're using costs money. Okay, so obviously you want to be efficient as you can and use as little of that as you need. So you look at the traditional profile of a typical long-running Java app starting up. You'll get a resource throughput response, something like this. So to start with, there's a lag between resource usage and throughput getting up to speed, which is obviously time you're paying for but not being able to utilise. And then you've got an overshoot. So you've got extra resource, CPU, memory usage, but no gain in throughput until it's roughly stabilised in the long run, where your resource usage equalises to a steady state, and everything's ticking along nicely, everything's been optimised. So there's that red bit we don't like that represents inefficiency, resource that we're paying for but not utilising. So this was our container graph on superimposed on the demand capacity graph over time. As you see, initially, in our simple view, we drew the red bits above the demand that we were wasting. In reality, we put in all the other red bits from the wasted, slow startup and inefficient resource usage. It becomes a lot redder, which is not good. So we want to optimize that and tune the JVM to use that efficiently. So demands on running a cloud. So you need fast startup, obviously. Get that red as small as possible to the left-hand side. Minimal memory footprint. So reduce the amount, minimal memory you need to run efficiently without too much loss in throughput. Similarly for CPU usage. And small deployment size, small footprint. And also optimizing your idle state resource usage. So when your microservice or whatever it is not actually processing requests, it goes into an idle state where it's using the least amount of CPU, heap, memory, etc. As it needs. So in an ideal world, then, you'd have a demand curve like this, roughly. So the resource use and throughput as far to the left as we can. There's no overshoot and wasted resource, and it quickly gets up and going for efficiently using the resources available. So that's what we want. So introducing OpenJ9. So OpenJ9 is so Eclipse OpenJ9. We open sourced it in September 2017 in the Eclipse Foundation. So it can be found at eclipse.org/OpenJ9 and the GitHub source, open source for OpenJ9 is the GitHub Eclipse OpenJ9 repository, and the associated OpenJ9 OMR code is there as well in the OpenJ9 OMR repository. It's dual license EPL v2, Apache version 2, and it's open source, so users and contributors are welcome. Follow that URL and you can see how you can contribute. So a little history on OpenJ9 to start with. So first of all, OpenJ9 is nothing to do with Java 9. So OpenJ9 came from a team that was actually developing a Smalltalk VM, which was called K8. And when those developers moved onto a Java, they thought Java was a step backwards compared to their Smalltalk. But they knew that the new VM would be a step forward. Hence, J is 1 less than K, but the 9 is greater than 8 by 1. Hence, you get J9. Okay, so that's where it came from. Nothing to do with Java 9, because it happened way before that even existed. They had a background in mobile devices running Java ME. So their concentration was be able to work efficiently in this mobile small device environment. And of course, to run in that sort of environment, on a physical phone device that's small, you need a fast startup. There's not much memory on the phone, so you need minimal memory footprint. Again, the processors on those phones are not very big, so you need to be not too CPU hungry. They didn't have much storage on those old Nokia sort of phones. Small storage footprint required. And efficient, so that it doesn't drain your battery. And of course, that sounds familiar, doesn't it? From what we just explained, what we need for our running Java in containers. So let's take advantage of that by tuning OpenJ9. I'll take you through some steps now, specifically to tuning Eclipse OpenJ9 to your Docker container environment. Because remember, performance isn't just throughput. Especially in this environment, we know we need to consider resource usage, startup, ramp-up time, and footprint. So let's look at how we tune OpenJ9. So firstly, OpenJ9 supports a lot of the same basic command line arguments as hotspot, max, min, heap size, and all those sorts of things, but there are one or two differences. If you follow that link, there is a migration guide to help you move from hotspot to using OpenJ9. So the first option that will help you in this environment, the Xtune virtualized option on the command line. So this is to help tune for containers to optimize the CPU usage. It does several things. It makes the JIT more conservative to do only what it really needs to do to help save CPU usage. It affects the GC, the garbage collection, reducing its heap expansion rate, again, saving CPU. And when also used in combination with the share classes option, the AOT, the ahead of time compilation, is more aggressive on subsequent invocations of your application. So it will aggressively compile all your methods ready for the next startup, which is going to happen because these are microservices typically within a very short period of time. So all of those help also improve startup and ramp up, basically doing only what's needed to get going in this virtualized environment. The other thing this virtualized option does is enable VM idle management to help recognize the idle state better and minimize the CPU usage and memory usage. So all of that comes at a small cost in terms of loss and throughput. And obviously the J9 development team try and minimize that cost so that it's obviously outweighed very much so by the gains. So X quick start. So typically in the cloud container environment, you're dealing with short-running apps, functions, things like that, microservices. The default behavior of the is for Java applications is you're expecting a long-running Java application, and with that expectation, the JVM makes certain assumptions. When we know we're in a quick start mode where these things are more short-lived, you can enable this quick start, which then, obviously by its name, puts emphasis on improving the startup ramp-up time. So it tunes the JIT for short-running apps. It basically makes the JIT use a subset of its optimizations, so it basically disables optimizations for long-running apps, essentially, concentrating on the core stuff to get just what you need doing, but not doing the extra stuff which would be more beneficial for long-running apps. And also enables the AOT for all methods. Since it's a short running and would be running the same microservice many times, the AOT can be a lot more active and it's ahead of time compilation. So all that leads to a faster startup. Again, small trade-off in throughput, but it's all great for short-lived tasks. Okay, use container support, which is enabled by default. And this basically allows the JVM to adjust in the container environment the max heap appropriately based on the available memory. And it's on a scaling slider. So if it's less than 1 gig, it uses 50% for max heats. If it's between 1 and 2, it uses the size of memory minus 512. And if it's over 2 gig, it uses 75%. And that can be configured. That sliding range. And then the last option is the idle tuning GC on idle. And this helps reduce the memory footprint by releasing heap memory back to the system when idle is detected. So it's also more effective when used with the container support option. So again, reducing that resource usage. So those are the key sets of options that can help tune to most efficiently and cost effectively use your Docker containers appropriately in your cloud container environment. So JVMs, especially in this cloud environment, do a lot of repetitive work. Rebuilding the same class files, performing the same optimizations, and carrying their own JIT to do all the above. So in the In cloud environment, you've also typically got a lot of JVMs, you've got a lot of Docker containers, all running JVMs doing that same repetitive work. So let's see if they can work together, make those multiple JVMs work together and do something useful. So, sharing class content. So this is a class file. So as it stands, all mixed up like that, that's not a great way to store class information. However, with OpenJ9, it's split into two components, a ROM class and a J9 RAM class. This read-only part is position independent, so that'll be the same, that same class compiled in each of those VMs. The stateful part is obviously different. So here's a view of multiple JVMs, and you've got the stateful bit at the top, and all those duplicated threes of the read-only class files. All these classes are identical. Okay? You can see where we're going, can't you? So let's share them. Let's do that, shall we? That would make perfect sense, wouldn't it, logically? We've just reduced the memory consumption of that by a third across those containers. So you can do that using the share class option, which enables class sharing. You can optionally set the size of the cache, so in that example, 50 meg, and if not set, it defaults to 300 megabytes. So this is basically a ROM class file cache, basically. And if you do that, it reduces your startup and footprint by roughly 20%. That's pretty good. Very good. So how can you actually do that in your particular Docker container environment, say? So here's your Docker container with a single JVM there. You can configure a Docker volume. So to create a Docker volume, the Docker volume create with a name. Have the Docker image mount that volume. So use the -mount source, the Docker volume, and the target directory, which is the virtual target within your Docker container. So /cache in this case, this example. And then you want to tell the J9 VM to actually use the shared classes and cache them in that /cache directory. So to do that, you simply start your VM with the minus share classes :cache dir /cache. And you start all the VMs with that option within that Docker environment, and they're now sharing that read-only class information in that cache efficiently. So that's the key bits of information you need to know to optimize J9, and you can typically see benefits in many configurations over hotspot of sort of 20 to 30% in terms of resource and footprint usage. Oops. Never mind. Wrong way, sorry. Oh well. I don't know why it's skipping ahead. I think. Never mind, doesn't matter, I can talk to that one. Yeah, don't worry. It's so the previous slide, the one that flashes up and disappears for whatever reason, is basically the front page of the Adopt OpenJDK download site, where you can download all your binaries for Adopt OpenJDK, for all the latest versions. It's where my team works with the Adopt OpenJDK community to provide those free binaries for Adopt OpenJDK with OpenJ9. We put them through a huge pipeline of build and test pipelines to make sure they're quality binaries for your OpenJDK. And we release on all the latest updates every 3 months, every quarterly update, every PSU update, for all your vulnerability fixes, and it's free. And because it's an open community, you're also very welcome to help support and contribute to that community as well. So that's the binaries at Adopt OpenJDK. If you want support for your binaries, IBM offers a support offering for OpenJ9 called IBM Runtimes for Business. And if you go to that marketplace URL, you will find that offering, which will offer you support for your installations of OpenJDK with OpenJ9 binaries downloaded from Adopt. And here's some additional reading, so you can find the comprehensive OpenJ9 user docs, where all those options I mentioned are well documented. And there's an interesting article on JVM comparisons there, and a couple of links to explaining more about the class sharing options that I described. Okay, that's it. Any questions? Is there any people here that have downloaded OpenJDK with OpenJ9 and started playing with it at all? No? Well, please give it a try. Get all these benefits. Okay, brilliant. Thank you.